ladies and gentlemen. Let's continue our discussion of logarithms and deal with powers and roots, shall we? And in order to generate this idea, let's start out again with log, or rather 10, say, raised in the log in the base 10 of a, in which we know that this is equal to, what? This is equal to, Doug, is equal to a. Let's look at that number a and raise it to the nth power, shall we? And so if we are to multiply or raise this side to the nth power, then certainly we may take this side and also raise it to the nth power. And on the right-hand side, notice now we have a power of a power. So what then is our rule that we have dealt with in exponents? It has always been to, Don? To multiply those numbers. And there we have 10 raised to the, let me write it as n times the logarithm of a, okay? But what do we know about 10 raised to the log of a to the nth power? And again, using our definition, this is equal to what? A raised to the n power. Is that right? Therefore, looking at this statement, we have 10 raised to this power is a, and a to the n power is equal to this. Therefore, what is our conclusion? But that we may say that 10 raised to the log of a to the n power is going to be equal to what? This side right here, in which we have 10 raised to the n times the log of a. And again, if we have two numbers of the same base and they are equal, what must hold true about their exponents? They are, Bill? Equal. They are equal. And we then may say that the logarithm of a to the nth power is equal to n times the logarithm of a. And in fact, this is a very important statement which we have, in which a can be any number greater than 0, and in fact, n can be over the set of real numbers. All right? And this we may state as a theorem, in which, notice now what the wording of this theorem says, that the logarithm of a to the nth power is equal to n times the logarithm of a. All right? And this, again, is where n is over the set of real numbers. Let's look at a number of examples of this to make sure that we understand exactly what the theorem says. Well, here we have a problem which says find this number by logarithms. Now, we have been going through this business of estimation, and if you don't mind, in order to save a little bit of time, I'd like to skip that aspect of it, and let's then go right to our second step as we have been proceeding earlier, in which we have p then is equal to that number, 0.784 all to the 6th power divided by the 5th root of 0.000348. All right? And again, now let's state what we would like to find. Logarithm of p then is going to be equal to the logarithm of all of this of 0.784 all to the 6th power divided by, let's write this as 0.000348 raised to what power? Raised to the 1/5 power, okay? Now, looking at this, we see a number of our theorems of logarithms coming out of there, in which one of the theorems says that the logarithm of a over b is equal to the logarithm of a, which is this number raised to the 6th power, and since it's divided by here, our theorem tells us that we must what? Subtract. It's then minus the logarithm of 0.000348 all raised to the 1/5 power. Now, our theorem that we have just developed says that the logarithm of a to the n power is a times the logarithm of n. Is that right? And then here we have minus the same theorem. We have 1/5 times the logarithm of 0.000348. Okay? Now, this then is the number that we're looking for. Let's set it up so that we can handle this in a rather efficient way. Let's come over here and write the logarithm of 0.784 is equal to something. We know that its characteristic is what? It's negative 1. Is that right? Which we may write as 9 point some number minus 10. We can look that number up in the table. Notice now we want to multiply that by 6. So 6 times the log of 0.784 is going to be equal to some number. In fact, I'd like to rewrite that number over here, because I noticed on the right-hand side there, I need to take the logarithm of 0.000348. Now, notice that we want to divide that number by 5. And what then is the characteristic of 0.000348? We know that that characteristic is negative 4. And if we're going to divide by 5, well, another name for negative 4, of course, is what? We have been using what? 6 minus 10. What's another name for negative 4 that you would like to write in order to divide through here by 5, and in order to still have it in the pattern of some number minus 10? And what can anyone come up with there? Steve?
46.
46.
Times whatever the number is from the table, minus 50.
Minus 50. Does everyone agree with that? Okay. And because when we take 1/5 of that logarithm, 0.000348, we then want to divide this by 5, and then 5 into that 50 is going to give us our number of 10. Now let's then repeat that number. And these two numbers, we would like to do what with them? We would like to subtract, because we are subtracting their logarithms here. That then is the logarithm of p, whatever that number is, and the anti-log then is the number that we want. Does everyone agree? Now notice we have set up this entire chart or table before we looked any numbers up in our tables. In fact, I've already done this before the lesson started, and the logarithm of 0.784 turns out to be 9 point, and mantissa is 8943. Also, the logarithm of 0.00348 turned out to be 46.5416. So let me just include these numbers in here. Now, it's 6 times this number, and let's just multiply this from left to right as we normally do, or from right to left. 6 times a negative 10 is a negative 60. 6 times 3 is what? Check my arithmetic. 25 is that right? And then we have 54 and 2 is 56, is that right? 48 and 5 is 53. Now notice we're carrying this 5. 6 times 9 is 54, and 5 is 59.3658 minus 60. And what there is the characteristic? Negative 1. Let's rewrite that as 9.3658 minus 10, shall we? And the characteristic is still negative 1. Now here we would like to divide this number by 5. Now notice we have a positive number here. 46.5416 is all positive, minus 50. So we just divide from left to right. 5 into 46 is 9 point, and then we have 5 into 15 goes 3, 0, 8, and 5 into 16 goes 3 and a third, and that third right there, let's simply drop it because it's less than 5. And 5 into 50 goes what? There's negative 10. And let's then simply repeat that number, 9.3083 minus 10. And now we want to subtract. And when we subtract, we have 10, negative 10 from negative 10 is 0. 3 from 8 is what? 5. 8 from 15 is 7. 5, 0.0. 9 from 9 is 0. Now, we would like to take the anti-log of this number. I have already done so, and it turns out to be 1142. And what then must our number be in order to give us a characteristic of 0? Bill?
1.142.
1.142. Notice that our answer is very close to the number 1. And looking at the original problem, which it's a rather messy-looking number, I'm not sure that one's intuition would say that that estimation is close to the number 1, but in fact it turns out to be 1.142. Let's look at another type of situation that I think is quite important. Here we have a problem which says, how many years will it take to double an investment of $1,000 compounded quarterly at 6% per year? Now, any kind of interest problem that you have done before this has always been what we call simple interest. And it's only now that you have a tool of logarithms that will enable you to handle a problem that involves compound interest. All right? And the formula that we use to determine that is given to us right here, in which A then is our final amount of money, and P is our principal, R is the rate per year, the percentage rate, written as a decimal, N is the number of conversion periods. And so since we are compounding quarterly, N in this problem is going to be what? 4. All right, well, we want to double our money. Start out at $1,000, and we want to end up with $2,000. Is that right? It's equal to 1,000 times 1 plus 0.06 over 4, all raised to the 4t power. And the problem is to find that number t. Well, we can divide both sides here by 1,000, and we have what? 2 then is equal to, and here we have 1 point, and 4 into 0.06 is what? 0. 1 and what? 0.15 all raised to the 4t power. Now, here we have two numbers. If a is equal to b, one of our statements that we said earlier, one of our assumptions was what? If a is equal to b, then what can we say about the logarithms of those numbers? Therefore, the log of a must be equal to the log of b. Is that right? So let's then take the logarithm of both sides in base 10. And here we have then the logarithm of 1.015 all raised to the 4t power. Now, using our theorem that we just developed earlier in this lesson, we have here the logarithm of a to the n power is n times the logarithm of a. All right? Now, we'd like to solve this equation for t, and t then is going to be equal to, just think of these as numbers, and there we have the logarithm of 2 divided by 4 times the logarithm of 1.015. Okay? And let's just find out what this number t is. Well, the logarithm of 2, I have already determined that, and it is 0.3010 divided by 4 times the logarithm of 1.015. I've already determined that is 0.0065. And from here on out, it's just arithmetic. In fact, we can do this by logarithms if we want. Well, let's just see how far we can get without doing so. 4 times 0.0065 we can do in our head. 4 times 5 is 20, and that's what? 26, is that right? With a 0 there. Let's multiply top and bottom by what number? How about 1,000, is that right? So that then is 301 divided by 26. I've already done this arithmetic out before the lesson started, and it turns out to be 11.57. All right, 11.57. And the question asks, how many years will it take to double your money? And notice it turns out to be around 11 and a half years of compound interest quarterly, compounded quarterly at 6% per year. And it takes around 11 and a half years to double your money. Of course, this problem started out with $1,000 and you end up with $2,000. You started out with $1 million. At the end of 11 and a half years, you'd have $2 million. Now, the important thing here is not so much the rate at which it is being compounded, but rather the interest. And in fact, if you take, say, the interest rate from 6%, say, down to 5%, I think the figure is close to 15 years. The difference between 11 and a half to 15 years by just lowering it 1 percentage point. But in fact, if you compound it, say, monthly or even daily, the number of years that it would do that would be very close to 11.57. It will not affect the time too much. Let's look at another problem. Here we have a radioactive isotope decays according to this formula. Q equals Q sub 0 times e to the negative 0.04 t power, where e is approximately 2.718. Now this, for the first time, you've seen another irrational number, which is called e. We're going to say more about this number as you proceed in mathematics. It says find the half-life of the isotope. That is, find t when Q is a half of Q sub 0. You start out with some amount of material. It's decaying at a constant rate. How many years will it be before it is then half of what it originally was, is the question. Okay? Well, let's see now. Q is a half of Q sub 0, so a half of Q sub 0 is what we want to end up with. It then must be equal to Q sub 0 times e raised to the negative 0.04 t power. All right? Right here, let's divide both sides by what number? By Q sub 0. And we have a half. Let me write a half as 0.5. It might be more convenient. Is equal to e raised to the negative 0.024 t power. Again, if a is equal to b, then what can we say but that the what? The log of a is equal to the log of b. So the log, now here we are still in base 10, is equal to the log on the right-hand side of e raised to the negative 0.024 t power. Again, using the theorem that we have just developed, on the right-hand side, the logarithm of a to the n power is n times the logarithm of, in this case, the number e. Okay? Again, we're solving for t. Therefore, t is going to be equal to, and here we have the log of 0.5 divided by a negative 0.024 times the logarithm of e. Is that right? Now, these are just numbers. Let's think of these as numbers. And the log of 0.5 I have already computed, in which it turns out to be 0.6990 minus 1. And for the first time, I'm going to treat this as a positive number minus a negative number. Let's continue in the next step here in the denominator. Times the logarithm of e, I have already computed as 0.4343. Now, 0.6990 minus 1 is what number? If you were to subtract 0.699 minus a 1.000, you'd have what? A negative, what? 0.3010. Let's take that out to 4 places. In the denominator, it's a negative 0.024 times, and here we have a 0.4343. Again, this is a problem in arithmetic. We can take the logarithm of the numerator and the logarithm of these two numbers and continue in that fashion. I don't want to take the time to do that. A negative number divided by a negative number is positive, and I have already done this calculation, and it turns out to be 28.28. And this number is in years, all right? So our isotope then is going to require 28.28 years before it is half of what it originally is. Yes. All right? And so this is exactly what we end up with by this method. Now, the reason I did this problem was to indicate that right here, for the first time, in fact, perhaps the only time, we will deal with 0.6990 minus 1 and treat that as a negative number. In all of our other cases, we've always thought of the mantis as being positive, and the characteristic was treated separately. Well, let me give you your homework assignment, which I'd like you to practice some of these problems. This will be assignment